And now in this lecture we'll find out the area of a circle using two different methods. In the drawing we have a circle. This is called BA, is equals to 13 units in its length. This is line segment BC, is equals to 6 units in its length. This is line segment CD, is equals to 18 units in its length. This is angle ABC, that is a right angle. This is angle BCD, that is also a right angle. Again, our task is to find out the area of this circle. So we start with the first method, and we define the center of this circle. This point is point O. Those two angles are defined as one-sided interior angles, and the sum of those two angles is 180 degrees, and therefore those two angles are located between the parallel lines BA and CD. According to Rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing we have line A, line B, and line C that cuts the two lines A and B. Those two angles alpha and beta are defined as one-sided interior angles because they are located from the side of the side line C. And they are located between the side line A and B. Therefore, they are defined as one-sided interior angles. The sum of those two, if the sum of those two one-sided interior angles is equal to 180 degrees, that is to say, if alpha plus beta is equal to 180 degrees, then line A is parallel to line B. Therefore, we can implement Rule 27 in our drawing. Why? Because in our drawing, those two angles are defined as one-sided interior angles. 90 degrees plus 90 degrees is 180 degrees. So the sum of those two one-sided interior angles is equal to 180 degrees. And therefore they are located between two parallel lines. That is to say, BA, line segment BA is parallel to line segment CD. So as you know, if you found out that line segment BA is parallel to line segment CD according to Rule 27. So in the next step, we will do a construction. That is to say, from point O, that is the center of this circle, we'll do perpendicular on CD, and we will extend the perpendicular by straight line until it touches AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, and side CD, this point is point M. We extended the perpendicular OM by side line until it touches side BA. Because of the fact that CD is parallel to BA according to Rule 27, it means that the perpendicular from point O on CD will be also perpendicular on BA. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Because they are parallel to each other, the perpendicular OM on CD will be also perpendicular on BA. We define the touching point of the perpendicular from point O and BA. This point is point N. So by doing this construction, you can do quadrilateral CB and M. Inside this quadrilateral CB and M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this 4 pieces again. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its size. Anyway, this angle equals to 90 degrees in its size, according to rule 3 also. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in quadrilateral BCMN, we have 4 angles. Therefore, according to rule 5, this quadrilateral is a rectangle. Quadrilateral BCNM is a rectangle according to rule 5. Here we can implement rule 19. Repeat on rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. So in the moment we have a circle, point O is the center of this circle. This is chord AB, that could be any chord of this circle. From point O, we go perpendicular OM on chord AB. And according to this rule 19, the perpendicular OM on chord AB bisects chord AB. That is to say, it divides chord AB into 2 halves. The first half is AM and the second half is MB. And of course, AM equals to MB. So we can actually implement rule 19 in our drawing. Why? Because in our drawing, we have perpendicular OM towards chord BA. And according to rule 19, perpendicular ON bisects chord BA. Again, according to rule 19, perpendicular ON bisects chord BA. That is to say, it divides chord BA into 2 halves. BA in total equals to 13 units in its length, therefore each half must be equal to 13 over 2, that is 6.5. So the first half BN equals to 6.5 units in its length, and the second half BA, the second half NA must be also equal to 6.5 units in its length. We already found out that quadrilateral BCMN is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. So CM equals to 6.5 units in its length. In the next step, we do another construction. That is to say, from point A, this is point A, from point A we go perpendicular on CD. Again, from point A we go perpendicular on CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we created here quadrilateral NMLA. If you focus on the perpendicular ON this angle equals to 90 degrees according to our construction, and according to rule 3, the sum of the angles on the lower side of the straight line NO at point M must be equal to 180 degrees. So which angles we have at the lower side of the straight line NO at point M? We have this angle that is right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NMLA, we have 4 right angles. Therefore, according to rule 5, quadrilateral NMLA is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NMLA, in rectangle NMLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. So ML equals to 6.5 units in its length. What is the length of this small line segment LD? From the drawing, it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So I did not know if I found out that the length of the short line segment LD is equal to CD minus CL. So LD in total equals to CD. CD equals to 18 units in its length, according to what is given in the question, minus CL. CL equals to 6.5 plus 6.5 is 13. So CL is 13. So in total, LD equals to 18 minus 13 is 5. LD equals to 5 units in its length. LD equals to 5 units in its length. In the next step, we will extend line segment CD by side line until it touches the circle. And we will define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we get here chord TD. This is chord TD, and OM is a perpendicular from the center of the circle, and according to rule 19, the perpendicular OM bisects chord TD. Again, the perpendicular OM bisects chord TD. That is to say, TM equals to MD. TM equals to MD. According to rule 19, TM equals to MD. What is the length of MD? MD in total equals to 5 plus 6.5. That is 11.5. So TM equals to MD, and MD equals to 11.5 units in its length. And from this equation, we derive that TM also equals to 11.5 units in its length. This is line segment TM. This equals to 11.5 units in its length. But TM equals to TC plus CM. TM equals to TC plus CM. So I'll write it down. TM equals to TC plus CM. So Tm equals to Tc. Tc is the missing side, so we leave it as it is, plus Cm. Cm equals to 6.5. Cm equals to 6.5. So Tm equals to Tc plus 6.5. But Tm equals to 11.5. So 11.5 minutes in its length. So we substitute Tm by 11.5 and we get that 11.5 equals to 6.5 plus Tc. So 11.5 equals to 6.5 plus Tc. Here we subtract 6.5 from this equation and we get that the missing side Tc is equal to 11.5 minus 6.5 is 5. So Tc equals to 5 units in its length. This is the short line segment Tc. This equals to 5 units in its length. In the next step, we will extend line segment BC until it touches the circle. We will extend line segment BC by straight line until it touches the circle. And we will define the touching point of the extended line segment BC with this circle. This point is point Q. Here we can implement rule 15. Why? Because we have chord BQ that intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. The intersection point occurs at point C. So repeat quickly on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true that AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. In this moment the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. So as I mentioned before, we have chord BQ that intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. So it is known in our drawing, we have chord BQ intersects with chord TD at point C. The intersection point occurs at point C. So all the requirements for rule 15 are satisfied, and therefore we can implement here rule 15. According to rule 15, the following equation is true: that TD times CD equals to BC times CQ. Repeat again. Chord TD intersects with chord BQ at point C. Therefore, according to rule 15, the following equation is true: that TD times CD equals to BC times CQ. Actually, it is TC times CD. It is TC, this is line 7 TC times CD equals to BC times CQ. Again, according to rule 15, the following equation is true: that TC times CD equals to BC times CQ. TC is 5 times CD. CD equals to 18 units in its length according to what is given to the question. So in this side of the equation we have 5 times 18 equals to BC times CD. BC is 6. BC times CQ. BC is 6 times CQ. CQ is the missing side, so it is. So in total, according to rule 15, I have found out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that the missing side CQ equals to 18 minus 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is line segment CQ. This is line segment CQ. This is equals to 15 units in its length. In the next step, we will join points Q and A together by straight line. Again, we will join points Q and A together by straight line. Join points Q and A together by straight line. By doing this construction, relative peripheral ABQ, peripheral QBA, or ABQ, it is the same. Peripheral QBA is a right angle, and peripheral angle QBA subtend on chord QA. Again, peripheral QBA subtend on chord QA. So here we can implement rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing, you have a circle. This is peripheral angle MAN that is equal to 90 degrees in size. And therefore, according to this rule 9, peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of the circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 15 in our drawing, rule 5 in our drawing, because we have peripheral angle QBA that is equal to 90 degrees in size, and therefore peripheral angle QBA must subtend on the diameter of the circle. Peripheral angle QBA subtend on QA, therefore according to rule 5, peripheral angle chord QA must be the diameter of the circle. So if now we found out that chord QA is the diameter of the circle according to rule 5. The diameter of the circle, of course, equals to, it is twice as long as the radius. So if we define the radius of this circle as r, then the diameter must be equal to 2r. So QA equals to 2r. QA equals to 2r. In the next step, we'll implement the Pythagoras theorem on the big right triangle, triangle ABQ. So I copy triangle ABQ in the new page, and we'll implement the Pythagoras theorem on this right triangle, triangle ABQ. Side AB equals to 13 units in its length. Side QB equals to 16 plus 5, that is 21. And the hypotenuse AQ equals to 2r. It is the diameter of the circle that equals to 2r. Again, BQ equals to 6 plus 15, that is 21. AB equals to 13 units in its length, according to what is given as the question. And the hypotenuse AQ is the diameter of the circle, this equals to 2R. Here by PT is the abbreviation for Pythagoras theorem. This, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle ABQ, AQ squared, that is the square of the hypotenuse, must be equal to AB squared plus BQ squared. AQ equals to 2R, therefore AQ squared equals to 2R squared, that is 4R squared, and it is equals to AB squared. AB equals to 13, therefore AB squared equals to 13 squared, that is 169 plus BQ squared. BQ is 21, therefore BQ squared is 21 squared, that is actually equals to 441. So in total we found out that 4R squared equals to 169 plus 441. So 4R squared equals to 441 plus 169 is equal to 610. So in total we found out that 4R squared equals to 610. Here we will divide this equation by 4. And we get that R squared equals to 610 over 4. 610 over 4 is 152.5. So we found out that R squared equals to 152.5. Our task is to find out the area of this circle. So the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of the circle must be equal to pi times the radius of the circle squared. The radius of the circle squared is R squared. So it is pi times R squared, and R squared is 152.5. So in total we should find out that the area of this circle equals to either 152.5 times pi square unit in its size, or in terms of numbers it is equals to 469.09 square units in its size. Repeat again. If we found out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 152.5 pi square units in its size, or in terms of numbers, it is equal to 479.09 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use the data that we have already found out in the first method. We have already found out in the first method that CQ equals to 15 units in its length and TC equals to 5 units in its length. So here we can implement all 26. Repeat quickly on all 26. According to rule 26 is true in any circle. In any circle, if two chords A, B, and C, D intersect with each other at point O, then the following equation, again, in any circle, if two chords A, B, and C, D intersect with each other at a right angle, chord A, B intersects with chord C, D at 90 degrees. And get C or B equals to 90 degrees inside. So if two chords intersect with each other at a right angle, then the following equation is true. That AO square plus BO square plus CO square plus OD square equals to 4R square. R is the radius of the circle. Again, if two circles intersect with each other, if two chords intersect with each other at a right angle, like in this drawing, then the following equation will be true. That AO square plus OB square plus CO square plus OD square equals to 4R square. R is the radius of the circle. So we implement all 26 in our drawing. First of all, we can definitely implement all 26 in our drawing. Like in our drawing, we have chord TD that intersects with chord BQ at 90 degrees. This angle equals to 90 degrees according to what is given us in the question. Again, chord BQ intersects with chord TD. Chord BQ intersects with chord TD at 90 degrees at point C. So all the requirements of rule 15 are satisfied, and therefore can implement here, all the requirements of rule 26 are satisfied, and therefore we can implement here all 26. According to rule 26, the following equation will be true. TC squared plus CD squared equals to TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. This is according to rule 26. And again, according to rule 26, TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225, equals to 4R squared. This equation is the implementation of rule 26 in our drawing. 25 plus 225 is 250, and we have 324 plus 36 is 360, equals to 4R squared. 250 plus 360 is 610, equals to 4R squared. Here we divide this equation by 4, and we get that R squared equals to 610 over 4 is 152.5. The area of the circle equals to pi R squared So it is pi, and r squared is 152.5. In total, we found out that there that we are looking for this question, that is there of the circle, is equal to either 152.5 pi square unit in its size, or in terms of numbers, it is equal to 479.09 square units in its size. So in both methods, we arrive to the same results. We found out that the area of this circle is equal to either 152.5 pi square units in its size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finished with the second method. The next step, I'm sorry, the lecture, we'll start with the first method, of course. Our task in this question is to find out the area of this circle. We found the area of this circle using two different methods. So in the first method, first of all, in the drawing we have a circle. This is called BA. This is equal to 13 units in itself. This is line 7 CD. This is equal to 18 units in itself. This is line 7 BC. This is equal to 6 units in itself. This is angle ABC, this is a right angle. This is angle BCD, it is also a right angle. Again, our task is to find out the area of this circle. So first of all, those two angles are defined as one-sided interangles, and the sum of those two angles is 90 degrees plus 90 degrees is 180 degrees. And according to rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. That is to say, BA is parallel to CD. Again, BA is parallel to CD according to rule 27. So in the next step, we define the center of this circle. This point is point O, and from point O, that is the center of the circle, we do perpendicular on CD. So this angle comes to 90 degrees, and this angle also comes to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. We extended the perpendicular until it touches chord BA. And we know that the perpendicular on CD must be also perpendicular on BA. Why? Because they are parallel to each other. Again, because the side CD is parallel to side BA, the perpendicular to side CD must be also perpendicular to side BA. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the rules dimensions. We define the touching point of the perpendicular from point O and chord BA. This point is point N. So we have here quadrilateral NMLA. In the upper quadrilateral BCMN, this angle equals to 90 degrees, this angle also equals to 90 degrees according to what is given as the question, and this angle equals to 90 degrees, and therefore if we focus on the upper side of the straight line NO at point M, here the sum of the angles must be equal to 180 degrees. So each angle we have at the upper side of ON at point M, we have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And so in total, in quadrilateral BCMN, we have 4 right angles. Because this angle equals to 90 degrees, also according to our construction. So we have 4 right angles in quadrilateral BCMN. And therefore, quadrilateral BCMN is a rectangle. We can implement here rule 19. According to rule 19, the perpendicular from the center of the circle towards any chord bisect the chord. So the perpendicular ON bisect chord AB. Chord AB equals to 13 units in its length. Therefore, each half must be equal to 6.5. The perpendicular ON bisect chord AB. AB is 13, so the perpendicular ON bisect chord AB into two halves. Each half must be equal to 6.5. So BN is 6.5 and A is also 6.5. So in rectangle BCMN, the opposite sides are equal to each other. So side BN equals to side CM. But BN is 6.5, therefore the opposite side CM must be also equal to 6.5 in its length. In the next step, we did another construction, that is to say, from point A, we draw perpendicular on CD. Again, from point A, we draw perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we can do quadrilateral MNLA. In quadrilateral MNLA, this angle equals to 90 degrees. This angle is also equals to 90 degrees according to our construction. If we focus on the upper side of the straight line NO at point M, here the sum of, if you focus on the lower side of the straight line NO at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have is the lower side of NO at point M, we have this angle that is the right angle, plus this missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in quadrilateral MNLA we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral MNLA we have 4 right angles, and therefore quadrilateral MNLA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MNLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing 97 LD? LD equals to CD minus CL. Again, CD minus CL equals to LD. LD equals to CD minus CL. So LD equals to CD, CD is 18, according to what is given in the question, and C minus CL. CL is 6.5 plus 6.5, that is 13. So in total, ND equals to 18 minus 13, that is 5. LD equals to 5 units in its length. In the next step, we extended 97 DC until it touches the circle. Define the touching point of the extended 97 DC. With this circle, this point is point T. By doing this construction, we get a called TD. This is called TD. So here we can implement rule 19. According to rule 19, the perpendicular OM from the center of the circle, that is point O, bisect chord TD. Again, the perpendicular OM, that is from the center of the circle, bisect chord TD. That is to say, TM equals to MD. Okay, according to rule 19, TM equals to MD. So TM equals to MD, and TM equals to MD equals to 6.5 plus 5, that is 11.5. MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we will derive that TM equals to 11.5. This is 97 TM, is equals to 11.5 units in its length. But TM also equals to TC plus CM. TM equals to TC plus CM. So TM equals to TC, TC is the missing side of limited cities, plus cm. cm equals to 6.5 units in its length. So tm in total equals to tc plus 6.5. But tm equals to 11.5. So we substitute tm by 11.5 and we get that 11.5 equals to 6.5 plus cm. Again, 11.5 equals to 6.5 plus tc. So note that 11.5 equals to 6.5 plus tc. Here we subtract the 6.5 from this equation and finally found out that the missing side tc equals to 11.5 minus 6.5 is 5. So this is the missing 97 tc. This is equal to 5 units in its length. In the next step, we extended 97 BC by straight line until it touches the circle, and we define the touching point of the extended 97 BC with this circle. This point is point Q. In the next step, we actually implemented all 15 in our drawing. In our drawing, we have chord TD that intercepts with chord BQ at point C. Again, chord BQ intercepts with chord TD at point C. Therefore, according to rule 15, the following equation is true that TC times CD equals to BC times CQ. Again, according to rule 15, the following equation is true that TC times CD equals to BC times CQ. TC is 5 times CD is 18. So in this side of the equation we have 5 times 18 equals to BC. BC is 6 times CQ. CQ is 15. So in total we found out that 5 times 18 equals to 6 times CQ. Here we divided this equation by 6 and finally found out that CQ, the missing side CQ, equals to 18 over 6 is 3 and 3 times 5 is 15. So this is 97 CQ. This is equals to 15 units in its length. In the next step, we join points Q and A together by a straight line. Again, we join points Q and A together by a straight line. By doing this construction, we can there rectangle QBA. Rectangle QBA equals to 90 degrees in its size. And according to rule 5, any rectangle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So rectangle QBA equals to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Rectangle QBA subtend on QA, and therefore according to rule 5, QA must be the diameter of the circle. So QA is the diameter of the circle according to rule 5. So the diameter of QA is twice as long as the radius. If the radius is r, then the diameter of QA must be equal to 2r. In the next step, we implemented the Pythagoras theorem on this right triangle QBA. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side BQ equals to 6 plus 15, that is 21. Side BA equals to 6.5 plus 6.5. It is given us a question that BA equals to 13. And the hypotenuse QA is the diameter of the circle, that is 2r. Okay, this is the right triangle QBA that comes from the original drawing. BQ equals to 21 units in its length, BA equals to 15 units in its length, and Q, the hypotenuse QO, the hypotenuse QA is the diameter of the circle, that is 2r. So in this right triangle QBA, according to the Pythagoras theorem, QA squared, that is the square of the hypotenuse, equals to BQ squared plus AB squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to AB squared. AB is 15, therefore AB squared is 15 squared, that is 169, plus BQ squared. BQ is 21, therefore BQ squared is 21 squared, that is 441. So in total, we found out that 4r squared equals to 169 plus 441. 169 plus 441 is 610. So in total, we found out that 4r squared equals to 610. Here we divided this equation by 4 and finally found out that r squared equals to 610 over 4. 610 over 4 is 152.5. So r squared equals to 152.5. Our task is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. But r squared equals to 152.5. So we substitute r squared by 152.5, and if I found out that the area of our circle equals to either 152.5 pi square units in size, or in terms of numbers, the area of this circle equals to 479.09 square units in size. So we finish with the first method. In the next step, I actually presented to you how to find out the area of this circle according to the second method. In the second method, we used with the fix that we already done in the first method. In the first method, we actually found out that CQ equals to 15 units in itself, and TS equals to 5 units in itself. So here, we used we implemented rule 26 in our drawing. According to rule 26, rule 26 is true in any circle. In any circle, if two chords A, B, and C, D intersect with each other at a right angle, that is to say at 90 degrees, here, chord A, B intersects with chord C, D at 90 degrees. This angle equals to 90 degrees in size. So if two chords intersect with each other at a right angle, exactly like in this drawing, then the following equation is true. That A all square plus B all square plus C all square plus D all square equals to 4R square. R is the radius of the circle. But again, if two chords A, B, and C, D intersect with each other at a right angle, exactly like in this drawing, they intersect with each other at 90 degrees, then the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. R is the radius of the circle. So we can implement rule 26 in our drawing. Why? Because in our drawing, chord BQ intersects with chord TD at 90 degrees. This angle equals to 90 degrees according to what is given us in the question. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. According to rule 26, the following equation will be true. That TC square plus CD square plus BC square plus CQ square equals to 4R square. Again, TC square plus CD square plus BC square plus CQ square equals to 4R square. And again, according to rule 15, the following equation is true. That TC square plus CD square plus BC square plus CQ square equals to 4R square. R is the radius of the circle. TC is 5, therefore TC square is 5 square, that is 25, plus CD square. CD equals to 18, therefore CD square is 18 square, that is 324, plus BC square. BC is 6, therefore BC square is 6 square, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 square, that is 225. So in total, we found out that 25 plus 324 plus 36 plus 225 equals to 4R square. 25 plus 225 is 250, and 324 plus 36 is 360 equals to 4R square. So in total, we found out that 250 plus 360 equals to 4R square. 250 plus 360 is 610, so in total we found out that 610 equals to 4R square. Here we divided this equation by 4, and we found out that R square equals to 610 over 4 is 152.5. So R square equals to 152.5. Therefore, this circle equals to pi times the radius of the circle squared, that is pi R square. R is 152.5, so we substitute R square is 152.5, therefore we substitute R square by 152.5. Actually found out that there of this circle, that we are looking for this question, it is equal to either 152.5 pi square unit in its size. In terms of numbers, the area of this circle is equal to 479.09 square units in its size. Okay, thank you very much.